All right, so after we've had a thorough understanding and detailed discussions about what a function is and some other details, some more advanced details regarding function, now it's time to get into understanding another important aspect, another important feature of a function, the graph of a function. Okay, and so this is a very important feature of any function that I have decided to create that in a separate video lesson here, even though it's supposed to be a continuation of the discussion topic on functions. Okay, so here we're looking at graph of a function. All right, and so I have to make a certain agreement right here. So I have to be clear that this video lesson, this video lecture in particular, is aimed at the audience, at the students who are in the pre-calculus level or at the college algebra level. And so I will start out showing the concept of graphing a function again, but allow me to assume and skip a few elementary steps where you have learned that before in the courses before. So I'm not going to be as basic when I show how to graph a function. I'm not going to go as basic as how you've learned that prior to this class, because I believe the idea of graphing a function has been introduced quite a few courses before you enter the pre-calculus here. However, it's still a good idea that I reinforce that a couple generalities of the idea of graphing a function, or as well as representing a function as a graph. And so allow me to still design some of the basic examples showing from the basic steps how we construct a graph. But then I'm not going to be as basic. I'm not going to go as ultra basic as those courses back in elementary algebra that showed you how to build a graph, how to construct a graph of a function. And then once I was able to point out successfully that generality about the graph, then at that point we're going to start picking up on the more advanced understanding in terms of the graph of a function, so that it will make the better transition into the rest of the course again. Okay, because the rest of the course is going to contain a heavy components where you're going to have to keep looking a lot at graph for any function. Okay. All right, so now here we go. That's the idea. We're looking at the graph of a function. And just like I mentioned earlier, now I briefly mentioned it again. You must have seen how to graph some of these functions here prior to entering this course already. Okay, so take as much of those understandings that you have had in the past in here as possible. All right. So allow me to give my own interpretation about the graph of a function. So anytime in the way how I see it, and in the way how I show this to any students face to face, I would like to explain this as and I would like to have my students understand the graph of any function as a chart, as a visual chart, as a visual chart. You read a graph as you're reading a visual chart. Okay, so now let me first start out with this example over here. Let's now formally call that example 1. Okay, and we are given a function f of x. All right. In the following table. All right, so we have a function given as a table, or being given and then represented as a table. All right, so up at this point, you are not unfamiliar at all, and as a matter of fact, you've been quite introduced to the idea of a function sometimes being given as a table. So here we are. Let's go ahead and get started with an example where your function is given as a table. So here's a table. All right, so the x value and the output f of x, okay, and your function is as following. We have a few So now at this point in your understanding, then clearly speaking, the x column here, that's the way how the notation is indicating, then this x variable over here is the input. So needless to mention, okay. And so now I'm going to look at a few inputs over here, 1, 3, 0. Okay. And then your function, this table here represents that the outputs for f of x when input x equals 1 is going to give me a 2, and then for 3 it gives me a 7, and for 0 it gives me a 1. Okay, so anyone viewing this particular function shouldn't be surprised at all about this idea that a function is represented here as a table, and the rule is not clearly seen, but other than being represented right here in this function, in this table. All right, so I don't need to talk too much about what this function is. So now the idea allow me to switch to the other board of mine right there. The idea now is just to graph. Okay, graph f of x. Okay, so that's the only instruction, that's the only requirements of the problem, that's the only instruction asking us what to do for the problem. Graph f of x. Some textbook or some instructor might use a little more formal wording. Sketch the graph. Okay, sketch the graph of f of x. Some instructors, some textbook authors might use even more formal terms. The formal way of wording to say to make a clear instruction of what to do with that function given previously. Okay, so that's the idea. So now allow me to start bringing up my graphing space. Okay, I don't want I'm not skilled enough, so I don't want to draw my graphing space here on this board I'm writing here, but allow me to swing back on my other board, and then I'm gonna pull up my electronic graphing space like that. Okay. All right, so now here we go. There's my graphing space right here. So here's the idea of graphing. And I hope through this example, in case you haven't been explained before, in case no one explained this to you before, then now I hope this example of mine, even though it seems that we're rolling back to the basic, but I want to explain a couple generalities so that once you have caught this general understanding, then you should be able to make your own graph on any function. And that's the idea right there. Okay? And so it's just, I was saying earlier that I want you, the students who are studying with me, to see the graph of a function as a visual chart. So the table itself is already a chart. Okay? But now internationally, mathematicians worldwide have come to a tool. Okay? Have come to a creative tool that, so we're gonna put the axes on, just like what you're seeing here. We're going to put the axes on. So this time maybe let me put it in a real close zoom right here. Okay? We're putting the axes on. And so now I understand that very traditionally the horizontal axis, as you are seeing here, the horizontal axis very traditionally is regarded as the x-axis. And then the vertical axis here in our graphing space is regarded as, or is labeled as, the y-axis. I would like to make a clarification. Now, I have explained earlier in the earlier lesson that inputs and outputs do not have to always be x and y. Okay? Input and outputs do not have to always be x and y respectively. And I have explained that clearly. When you are fluent enough and flexible enough, and at this point, when I'm saying that anyone viewing this lesson should be a pre-calculus student, then your majority in mathematics should have grown a lot more than how you were in the previous courses. And so now be ready to accept the fact that you can flexibly assign any variable, any letter to name your input and to name your output. Okay? And so the point now is that when you're looking at a graphing space as seen below here, when you're looking at a graphing space like that, the horizontal axis is meant, this is the one international agreement. Doesn't matter if you're doing math in America, you're doing math in China, you're doing math in Vietnam, in Korea, anywhere in any corner in the world. as long as you're doing math. And the horizontal axis, as seen here, either you can see this version of mine or in a close-up version. The horizontal axis is meant to be displaying the input values. Okay, so now I'm saying it one more time, spelling out clearly. The horizontal axis, okay, is meant to display the input values. So now the impact of that now is that from this table is meant to have the x column. See here, the problem gave us, the problem already intended that the x variable is the input. But more generally, I want you who learns from this lesson, I want you to understand that x here is playing in the role of the input. And so now I'm going to bring these values, okay, and find its places, find their places on the horizontal axis first, okay? And so now let's look at the first value here, and at the same time, so allow me this time to still show the table here with my board, and you have to look at the small little graphing space here on the screen right here. But now when x equals 1, when the input value equals 1, this is how I'm seeing it. Okay, so this is where input value being 1 right here. So if we place it on the horizontal axis as set, then, and by the way, so I forgot to mention, but now I say it. So since this problem says the input is labeled as the x-axis, then yes, when you are making your own graphing space, the horizontal axis now should be labeled as the x-axis here. Okay, and then so in that way, continuing from what I was saying earlier, now on this x-axis, on this horizontal axis where we display all the input value, that value x equals 1 should be located right here. Okay, it should be located right here. Right now I understand that the graphing space of mine is a little small, but observe where my mouse cursor is moving right here. That's indicating this is where I put the x-axis. I mean the x value, the input x equals 1. Okay. But just inputting x equals 1 is not enough. Inputting x equals 1 is not telling the story, because now if you're looking back at the table, the whole idea now is that what happened to the output when x equals 1? What happens to the output when x equals 1? What happens here is that when x equals 1, the output is 2. All right, so now here we go. The general agreements, the international agreement among all mathematicians worldwide is that we're going to put the output value on the vertical axis. Okay, so according to this table, it's a chart as a table. The graph is a chart as a visual picture. Okay, so according to this chart right here, when x equals 1, we have a corresponding output being 2. So now in a graphical version, as you're seeing on this graph right here, when x equals 1, okay? Now, the problem itself, I also need to mention, the problem itself purposely did not label the variable of the output. It just indicated by some f of x, which is in functional notation. So now you can notate this. You can name this variable that represents the output as a y, or you can also have your choice of naming that a w, a t, a z, or whatever. Okay, but now once you have assigned a variable name for that, then this variable, any value to this variable is going to be found on the vertical axis right here. And this is what I'm showing that. Okay, and so now, so back together, so the two values, the inputs here and the output comes out as a 2. So the two values together makes up a point. The two values together give you 1 point. And now I'm going to say, that's the point right there. All right, so now hopefully, now all of a sudden you see that there's that point in green right here popped out right on my graphing space. But that's the idea. So here's the way how I'm reading it and understanding about it. See, this point is telling me that when x, the inputs equals 1, then the outputs, see, and from where this input is currently located at, it has a height. It has a height. So watch out for that way how I'm saying, because a lot of time I say height, a lot of time many other professors say height as well. It's indicating that the vertical height, and the vertical heights graphically represent the output value corresponding to that current input you're at. Okay, so that's why I was saying earlier it's a chart, it's a visual chart. Versus this table as a chart, you don't see much, but now you see a graphical display, you see a drawing, you see a display. Okay, with graphical representation and all that. And so now when you're at input 1 for x, okay, and just now earlier I was naming this output variable to be the y variable. So now needless to say, the vertical axis is where we display all the output value. That's where, so this vertical axis now is labeled the y-axis. Okay, so the reason I say this now is because anyone who arrives here at pre-calculus, you should start being a lot more flexible than that. All you do is keep in mind, all you need to do is to keep in mind that the horizontal axis is a place where you put all of your input values, and the vertical axis is where you put all of your output values. Okay, but you don't always have to name the horizontal axis here the x-axis and the vertical axis here the y-axis. You don't always have to do that. Okay, and as your mathematical career will grow, will continue to grow more advanced, there will be courses later, and maybe it's right here within this course that at some point later on, this axis here will be labeled the t-axis, and this axis here is labeled, the v-axis. There are so many applications out there. There are so many ways how you interpret it. But in the end, remember now, vertical axis displays the outputs, and horizontal axis displays the inputs. And so the way how you read, so look back at the screen point, it says, what it tells me is that when you are at, for this function, when you are at x equals 1, okay, then your output is at 2. It gives you a perfect way of seeing it. And once you see the picture, you start having a good sense about, okay, that's how high it is. Okay, and of course, when I'm saying that's how high it is, we only see 1 point so far. We have only seen 1 point so far, so it's kind of senseless to judge about how high it is. And wait until you see some other values, and you're going to start sensing how high that first point is compared to other heights. Okay, and so now you're ready, and anyone, after this thorough explanation of mine, hopefully I want you to catch that generality. Now we are ready to move on to the rest of the table. So now the rest of the table, we have a value when x equals 3. This is the input. The output comes out correspondingly is a 7. Okay? We didn't see the rule specifically, but the rule has already been represented and displayed in this table. And now we bring this table and transform that into a graphical display like that. So now when x equals 3, the output is 7. So guess what? Now you don't have to guess. Tell you what. This value has to be located on the horizontal axis, and this must be found on the vertical axis. And this output right here is the vertical height right here. And then where it is on the horizontal axis, together with how high it reaches or how low it reaches vertically, that will together make up a point. Okay, so now let's see real action here. So now when x equals 3, right here now, pay real good attention to this, to what happened to the point, right? Because right now I didn't put in the height yet, but right now on the x-axis we're at x equals 3. So let's have a look like that. Okay, so now my value here is a 7. Okay, so now all of a sudden right here on that I have a point that popped out like that. Okay, and so now back to what I was saying earlier, the graph. Now having a graph in seeing the graph in this graph here is the graphical transformation of from where the table was. This table was transformed into the graph. Okay, and I was saying earlier that having the graph now, that version of the table, that graphical version of this table makes it look better, makes it more understandable, and gives us a better sense about how high or how low a point reach. So now at least we have had 2 points on the graph. See, now I can say that, see, when x equals 3, we have a higher point, we have a higher value. Okay, and at least among the 2 points now, I can see that there's a rise. I'm also starting to introduce for you the whole purpose of why we need to see a graph. Because that purpose later on in our course, and when your mathematical learning gets more and more advanced like that, then you will be spending all your days looking at graphs and to analyze it. The work will, after a few couple examples here where I show you how to graph, then the rest of the time you're learning pre-calculus with me and the rest of your mathematical career, it's all about, here you go, a graph is given and you need to look at that and understand what it tells you and know how to analyze your graph, other than just, rather than just sitting there and make the graph and make the graph. We will no longer have to make the graph. Okay? And so now looking at this, the purpose of this graph so far, it tells me that, hey, at least I see so far is when x equals 3, the height comes higher. The output comes higher compared to when it was x equals 1. Okay, and so those are the 2 points. So once again, we have to put the x and the y value together, the input and the output together to make a point. But in the end, the way how I see that is at this input, there are that height being the output. Okay, all right, so now gladly this table representing our function, this table of values that represent represents our function is short enough, so we're only having one last entry to go. Okay, so now let's put that in. All right, so let's see, the next one is saying at 0, at the input 0. And see, I'm giving this example where the x values are completely unorganized. It's okay, it's okay. Okay, it's okay. A lot of times when we're working out with things, we don't always have time to sit down and organize values into a certain order. Now the reason we can organize the x values, the input values, simply because we recall from earlier understanding that input values are independent. So once we, in the end, being independent means we can choose them independently. And so a lot of time it helps if we organize them. But in a bigger amount of times, the greater amount of times, a lot of times we don't have time to sit down and organize out these values, keep them as random as they can. That's okay. So now in this table, I see another entry here. When x equals 0, let's find out what's happening. The output comes out correspondingly being 1. Okay, so when x equals 0, when the input is 0, output is 1 correspondingly. So now on the graph, right here, observe my mouse cursor. Okay, when the input is 0, okay, input is 0, the graph comes out, the output value comes out correspondingly being 1. So in that way, here's how I see it. Okay, now I put in that 0.1 right there. Okay, so another point just now popped out. Another point just now popped out. But now, welcome aboard, ladies and gentlemen. You have just now successfully made the graph of this function. You have sketched the graph. That's it. The graph here is telling you once again. So now, why is this graph so simple and so short? Because that's what this function is. That the function here is this function simply describes only 3 input values, and that's all we know about this function. So again, I would like to emphasize my point is that any graph of a function is just simply a graphical representation, and think of that as a graphical chart. Instead of seeing tables like this, we put it on a graphical chart so that you can see, hey, when x equals 0, when input equals 0, what's the output at? The output is at 1 for now. When input equals 1, the output comes out to higher, okay, being 1, being 2 here. And when outputs come to 3, when we give the inputs 3 for the function, we came out with an output being 7 right here. And that's all it tells. And immediately seeing these 3 points, you can start seeing that the function, as we increase, see, now the graph, the tool I'm using right now, the software, the program I'm using right now is smart enough to purposely organize, and it knows where to place it. And I don't mean to make you think like only machine can do this. When you're doing this on your own, it makes sense that this point have to come first in the graph, right? Because on the x-axis, 0 comes first, then 1, then 3. Our table representation can be sometimes out of order, okay, unorganized. But when we put things on the graph, then all of the inputs have to be in a certain order, because that's the way it is. Observe the horizontal axis again, the axis where the axis that I display all the inputs. The way it is, and you have learned this idea since long ago. It didn't have to wait until pre-calculus to understand. But when we put values on a line of numbers right here, when we put values on a line of numbers, then we have to put that in increasing order from the left to the right. So now on my horizontal axis that we put all of the input values there, then so from the left to the right, so it makes sense that this point has to come first. Okay, and then that point corresponding to an input x equals 1 has to come second, and then that last point here when x equals 3, it has to be the third point from the left to the right. So when you're actually doing that, when you're actually doing a hand sketch on your own, and by the way, I'm using this software program to make it feel like I'm really doing a hand sketch. Okay, that's the closest one I've found, so that we can work things out like pretending that I'm really doing a hand sketch. Instead of myself doing a hand sketch on the board, I don't feel comfortable with or confidence with my own hand sketch skill, and it takes me time to draw the axes and all that and make the grid. So leave it for the software. Okay, I'll leave it for the software. But now, so at this point, I hope you have seen a good enough generality of what it means by graphing. So the point now is that anytime you have a function, your function is given to you, okay, then the next good step is to get the table of values. The next good step is to get the table of values. And once you have the table of values, okay, now I'm not saying that you always need to have a table of values. Wait until when your experience become more advanced and more advanced, when you become a lot more mature than this instance. Then at some point when you feel confidence enough in your experience in math, then you can also skip the table. But as a good practice, as a high recommendation, once a function is given to you, and of course you're in the situation where you need to think about the graph, where you need to work with the graph or sketch the graph, okay, then once your function is given, then we need to come up with the table of values. This example itself was already particularly good in the sense that the function itself came already represented as a table. So it saved us some effort of constructing the table. But once you have the table showing input and output values, then the graph is just simply a graphical transform of this table. We go from table version to a graphical display version. That's all there is. Okay, and so that's the whole point of making a graph. So any function, of course, you've learned the idea. It's a rule. It takes an input to an output. See, and so now we display the inputs together with the outputs. Input as horizontal height, okay, and output as vertical height, and input is the horizontal value. And so together we make a point. And once you read that point, it tells you what's going on with the function output at that specific value. Okay, so that's all there is. The end of this example one. The end of this example one. I hope I didn't have to go too far to the ultra basic of that. But now I'm pretty sure you have seen in your past courses, before you enter this class right here, graphs that look even a lot more advanced than the one I just showed here, and you're starting to become nervous. Why is this graph so simple? What about those graphs I've seen in my courses? Mr. Professor, this graph looks a little too basic. Well, formally speaking, a graph like this is say scatter, okay, because the point is kind of scatter out. Okay, but Mr. Professor or Mr. Instructor, okay, why is this graph looking so simple? I've seen in my earlier courses, my prerequisite course before pre-calculus here, graphs that looks kind of like this, a line. Okay, what about those kind of graphs? How come I didn't talk about those? What about these kind of graphs right here? Okay, so now that's the reason why I want to take you to example number 2 right here. But so here's one thing. Before I step out to example 2, you must have heard about those terms, the linear functions, the graph of a linear function, the graph of an absolute value function, and the graph of a quadratic function. Okay, and so many names, so many terms you have learned in your past courses. Okay, the point of example 2 I'm about to show is just a general understanding. So be ready that I'm just simply giving you any function. Don't expect it's a linear, don't expect it's a quadratic, don't expect it to whatever, or once I wrote it down, whatever you recognize, just hold it to yourself. I just want you to understand just the standard understanding, the formal understanding that once you have a function given, then we need some sort of table values. And then once we have table values, we put those point on the graph. Okay, we display those points. Okay, but now I'm about to give an example to explain why we have those kind of graphs where it creates a nice, smooth drawing like this. because here it's just scatter points. This example, at the end of this example, it's just scatter points. Okay, but then what about those that you have seen in your past courses where it had those, nice drawing? Okay, sometimes it's line, sometimes it's bent shape like this, whatsoever. Okay, so let's head out for example 2. All right. And so now our goal is still to graph a function, but now I'm going to call that example 2. All right, so example 2. Now I'm going to be given, how about f of x, okay, equals, and it's just, I'm a little out of creativity today. I'm not in a good mood for having creativity, so I'm reusing that name f of x, but it's going to be a different f of x, it's no longer the same f of x in example 1. Okay, but so now let's look at our f of x function. It's defined as, and in this notation, so x is the input. I got to constantly remind you that after you have learned from my earlier video lessons about what a function is and how we use notation. So this function is named f, it takes input x. So now our function is defined as x squared minus 2x. Okay, so before I write down the actual wording of the problem, the requirements of the problem, okay, so what's being different from this example compared to the earlier example? What's the difference here? We have a function given, okay, okay, but the major difference here with the earlier one is the earlier one, your function was already represented as a table. But back then in example 1, we did not see the rule. We did not see the rule clearly stated. Here we have the rule clearly stated as an equation, as a formula. Okay, and this rule tells us what to do with the input. This function says for any input x, generally we're going to square the input and minus 2 times the input. Okay, and so that's why the function here can just be simply given with the rules clearly and explicitly stated here. And then from the beginning, there will be no table given. We built the table ourselves. We will build the table ourselves. Earlier examples, since the rule wasn't so clear, okay, the table was given instead. The table representation was given instead. All right. So in the end, yes, once we have that function given, I just want to say graph f of x. Okay, or formally speaking, sketch the graph of this function f of x. All right, and so now here comes the formal process again. So just like back to what I was saying, a graph is a graphical transform. It's a visual chart. Okay, any graph is a visual chart of your table values. The table of values itself is already a chart. Okay, but now we're going to transform that table of values into a graphical display, into a visual display like that. Okay, so now needless to say, that tells all that how important it is to have the table of values like that. Okay, sort of like we rolling back to the really core understanding. Okay, and so now let me quickly prepare my computer screen here before we advance on. Okay, so now we can call this input, the input variable x, and f of x. This column is for the outputs. Okay, and so I can go with some values, say for example -2, okay, -1, okay, 0, 1. Just a few, okay, just a few. All right, and so now this is how it makes it a little different with the, pretty much we're doing a similar example compared to those examples that you have done in your previous courses. But this is what makes it a pre-calculus student right here. I'm not going to go through the little steps, how you get these. I want viewers to get your own output values and fill it in here, okay? And so as you're doing this independently, I will also quickly spend some time do the calculation. But see, if this example was delivered in a more the elementary course right there in algebra, then you need to go show the calculation steps. Here we can skip that step. We skip all of that. Those are elementary steps right there. So now when x equals -2, all right, then our output here is +8. Okay, this is the same as f, substituting -2 in that. But how do we get this 8? I leave that for you to verify, and you can always pause the video and verify me, okay, and correct it and verify my information up here. Okay, so now when x equals -1, all right, then we have an output being 3. This means you just simply substitute -1 into the function, and our function has that rule clearly stated here. That's how it happens. Okay, and then when x equals 0, we have a, okay, we have a 0 as the output. Okay, we have a 0 as the output. And then so f of 0, we have these, and that's what it means right here. And when x equals 1, we have an output being -1. Okay, we have an output being -1. All right, and so now let's see how it works with table of values. So now at least, okay, don't be too worried about how far we need to go. Just for now, a few, good enough. And that's another thing I would like to emphasize right there. Okay, for if we're starting out from scratch, because you are I'm also preparing yourself I'm preparing you to work with the function that you haven't seen before at all. So when you're in that desperate situation, how many input values to choose? Okay, we'll have to explore. We'll have to explore, and that's why we're going back to a little bit of the basic side right there, and start building our foundation, from the ground up, so that hopefully you can build that solid foundation there for yourself. Okay, so now right now just 4 input values is good enough. Okay, so let's see how it works here with the. All right, so let's see how it works here. So I'm going to switch over to my graphing device here. All right, so now, once again, just like how I have already explained and how I have spent a lot of time explaining in the earlier example, the horizontal axis is where we display all the input values. Okay, and since the input values here is labeled as the x variable, and so the horizontal axis you see in this graph here, and that's why a lot of time you see me leaving all of these axes here empty without a label, because I want you to reserve that for you. If your problem, the labels, and if you name your input variable as the t variable or as the x variable, then the horizontal axis here gets the exact same label. Okay, and then if you put whatever you name for your output variable, then that's what you label for your vertical axis. Okay, so once again, vertical axis is to name all of the output values. Okay, so now when we are at all right, so now let me put the values on. When we're at x equals -2, okay, this input right here. All right, so I hope you're gonna pay your attention to this spot right here. So now -2. Now I have a point. -2 with output value being 8. Okay. So now, in case you have also see it, in case you wonder, and how come I don't mention about this? It's not important at this point, but you see, your past instructor in previous course must have mentioned that. You see, so you can also see the pair of x and y value, the pair of input and output value as a coordinate pair. In case you're strictly looking at the graph as just like a map, then each point on the graph has a coordinates pair. So input value comes first, comma, output value. Horizontal value comes first, comma, vertical value. That makes up the two values there, make up a coordinate pair. And that coordinates pair is what put that point on the graph at the correct spot, at the correct position. Okay, but being a coordinates pair is not the main aim. That's for the easier class. Okay, for us, we don't need to worry about that kind of thing. All I see here is that when we're at input x equals -2, our function reached to a height our function reaches to an output being 8. Our function reaches to an output being 8. All right, so now ready for some further advanced action. All right, so now I'm advancing down to the next one that I've had over there on my board right there, -1. Okay, so let's see, -1 is right here. Let's find out what's going to happen here. So -1. All right, so the point in green popped out just like how it was on the table of value we've had here. Okay, the table of value says, and according to our calculation, and I believe you should have spent your time verifying it, when x equals -1, we had an output being 3, and the graph just now showed it. Okay, and so now at this point, let's pick up the pace right here. And so thankfully we have software that can allows things to be a little faster, but allow me to finish entering the rest. So when x equals 0, okay, when x equals 0, we have a point right here. The output is 0. So that point, needless to explain, that's why it stays right at that origin. Because when x equals 0 and the height drops right down to there. Okay, and so we have the output being 0 and at inputs equals 0. So that's where that point meets right there at the origin. Okay, and so now one more point right here on our graph. We're looking at, and so far, you see right now with only 3 points, we don't see much. We don't see much about this graph is just like another scatter graph like the one we have seen in example 1. So nothing giving a fancy curve drawing and anything like that. I don't need you to worry about that right now. Okay, and of course 3 points is not enough. And so as I'm going through the steps right here, I want you to understand and think about the first generation of mathematicians when they are discovering the graphs of a particular function. That's what they do. That's what they did. Okay, and so now let's look at the next plotting entry right here. So when x equals 1, when the input value equals 1, when input values equals 1, maybe let me roll back to that point right there. When x equals 1 right here, I put my mouse cursor here to trigger your attention, to grab your attention right at x equals 1. And now I'm gonna put in the input. Okay, and then after that I'm putting in the output, and there the output this time sinks low. All right, so we've had 4 points in our table so far. Okay, we've had 4 points in our table so far. And then, well, basic idea, it's just the way how humans' mind evolved right here. Once we start seeing point and we know that we're looking at from these points from the left to the right, it's the way it is. It has to be from the left to the right, because that's how we can put the input values on an axis, on the line of values. And so from the left to the right, because the x values, the input values go small to large from the left to the right, then we notice the height changes according to the changes depending on where we're at here. So the height here, it was first at the first point on our list here, it was a high height here, a pretty high point, and then it drops down to only 3, and then it drops down to 0, and it keeps dropping. But is that a dropping down in a straight line? Does it seem to form a pattern? So now I'm talking about pattern. The idea, now I did not mention this in the earlier problem because there were 3 inputs anyway. But now with this function, we can keep putting in more inputs. Okay, that's why earlier I was saying, is this enough inputs? I didn't need anyone to worry about how many inputs is good, but now be aware in the back of your mind that as we're building something like this, we have to put in as many inputs as possible so that we can start recognizing a pattern. Okay, and so now with that, so now I'm starting to see it's forming a pattern, but it doesn't look like the pattern falling straight down in a line pattern. Nope, doesn't look like there's a line going through this. Okay, so now in that way, let's put in some more values. Okay, let's put in some more values. So how about x equals 2 right here? Let's see what's happening when x equals 2. Okay, so now back on my table, I can put another value here. Okay, when x equals 2. Okay, so let's see what's going to be happening here. Okay, so when x equals 2, we're looking at 0. Okay, and this means f of 2. And you can go ahead and verify me on that. Okay, we're looking at 0. All right, so now let's put that there on the graph. Okay, so here's on my graph right here. When x equals 2, so when x equals 2, we have another green point, but popped out right at y equals 0 here. This is just exactly consistent with what I've had. Okay, so we're starting to see as we keep putting more points in, more inputs in, and coming out with outputs. So that's what I was saying. That's why I was saying as we're putting more points in, we start noticing it's starting to be clear that it's no longer, it's not a line pattern, it's some kind of band pattern. But the point now is that's still not enough. That's still not good enough to recognize the shape of the graph. And so I'm going to go one more value. Okay, so what about my table here is a little short. So let me switch over to this board. And we can put in a few more values. So x, okay, and then the f of x, okay. And so now I can say, how about let's put in 3. Let's put in 3 right here. Okay, so with 3 right here, the output means f of 3. Okay, and then go ahead and spend your time doing this calculation independently. All right, the answer coming out for that should be a positive 3. Okay, it should be a positive 3 again. Okay, so input comes out with output being a positive 3. Okay, and so now I'm going to put that on my graph. When x equals 3, okay, right now there's no point yet. And then I'm going to spend some time putting that in my graph right here. All right, so now we had that 3, 3 right there. When input is 3, output is 3. Okay, so now just like what I was saying earlier, just exactly like how I was saying earlier, a graph is a visual chart of that table over here. The table itself, the table of values is already a chart, but the graph is just a visual chart. We transform this table of values into a graphical display right there. Okay, because it shows us what's happening when x equals 3, when x equals negative 2, okay, we have a height like this. When x equals negative 1, we have a height like this. We have an output like that. When x equals 0, so everything here displays exactly whatever happens in the table of value where I continue further. And at this point, when you're checking out that pattern right here, it start forming into some kind of trace. Okay. Now we've had only 1, 2, 3, 4, 5, and 6 pairs of input and output. We have only done about 6 inputs, and that gives out correspondingly 6 outputs, so that we have 6 points plotted here on the graph. Okay, let's go one more point right here. So what about when it's 4? Okay, when it's 4, so the output value for this, I can just simply remind you, and I'll leave that for you to do the calculation here. It means f of 4. Let's substitute 4 into your function. F of x equals x squared minus 2x right here. So once you've had your calculation, the final output should be 8. Okay, the final output should be 8. All right, and so now back on my graph. Okay. All right, so here we go. This is x equals 3. It already gave out outputs 3. So now one more value. See, when x equals 4 as for the input, okay, when input equals 4, it gave out outputs being 8, just like what it calculated. So now at least from the left to the right, we notice the heights of these the outputs value changes. It started out high, it drops out low, it drops down low, it even drops further to a negative height. See, negative height, and it hits back up. It rises, it starts rising back up. Okay, those points starts rising back up and start rising and keep rising. Okay, and so now think about how we were the first time doing a graph like this, and after we've seen enough trace of points here. And now when I'm saying the term trace of point, I mean you have to start setting yourself into that general convention. Look at graphs from the left to the right. Okay, I'm not saying that we always need to look at graphs from left to the right, but a really good amount of time that you have to look at graphs from the left to the right, because that's the way how values for the inputs are being organized from the left to the right, increasingly from the left to the right. Okay, and so now in that way, see, once you have seen enough trace, so think about you have a pencil and you place and try to trace that along these points like that, along these points from the left to the right. Let's see what kind of shape it gives us. Okay, and so now, all right, so now I'm going to start tracing. Okay, there you go. So here's the tracing. I'm using some kind of magic pencil to trace. This tracing is making it really precise, but that's how it is right there. All right, so as we trace along, see, those points now, as we're looking back right here with the actual graph, see, once we put on the curve right here, we notice all of these points form exactly into that kind of shape. And now that shape is, well, welcome to, maybe you have seen this before, maybe you haven't, but this is a formal graph where it's a nice, smooth curve right here. But at this point here, someone's starting to wonder, I mean, how do we know it's because we only, in the end, we only made how many points here? 1, 2, 3, 4, 5, 6, 7 points. How do we know so sure that it goes like that nicely, a bent curve like that? How do we know that if it's not going like a crazy zigzag, or how do we know that it's not simply just straight line connecting between these? Okay, good question. It's a very good question. So here's the thing. So now, in these days, any of you have strong enough technologies and all that. So you have your TI, the 83, 84 calculators. You have, you can hop on the internet, and come up with and there are tons of graphing tools, resources that are very powerful that being offered over the web right there. It can help you do a quick the graph, or at the worst, if you don't have advanced graphing devices, this is what I can tell you. We go back to our table and put more points in. The idea now is about the refinement. Okay, so first let me undo this tracing right here. How about if anyone does not believe my tracing, that it's gonna form into a shape like that? Because somebody might still be worried that what if it's just a straight line connecting down, straight line, straight line, straight line, straight line. Okay, so now I'm going to convince you that it has to form into a nice smooth bent curve. The idea you have to realize is that back in this table, between -2 and -1, we have already skipped a lot of values. We have already skipped infinitely many values between these. And the same story that goes here. Between -1 and 0, we have skipped a lot already. Okay, and between these. So now I use that term refinement, means let's try to put in more inputs, but let's choose those values between these. Okay, so that we can see, as we can put more points there, then it's better, it's easier to recognize the actual shape. All right, so I don't want to erase out and brutally fit more values in between these. So I'm going to continue my table of values on the other side of the board. Okay, so let's see how things happen. All right, so, and now we will need calculators as well. Okay, so think about between -2 and -1. -2 and -1. I can put in a -1.5. Okay, this is a value that's between -2 and -1. See, the more points we put in, the more inputs we put in, of course, we will consequently come out with outputs. That's what I meant by the more points we put in. The more points we put in, the more values we can have, the easier it is to recognize the shape of the graph. Okay, and then we can put in a values -0.5 right here, and I'm leaving this for you to do your own calculation because I don't have a calculator at the moment with me right now. Okay, let's experience, and you can help me fill out this as we're going along. Okay, and now we can still put in more values. So let me put this graphing space away so that you can see more of my board right here. Okay, and then we can put in +0.5, okay, we can put in a 1.5. We can put in all of those values in there. Okay, and so now I'm going to quickly step to my computer station to graph those output values right there. And I ask you, any one of you who studied this video lesson together with me, to come up with your own output values here independently as well. The more independent that you can be, the better you will learn. Okay. All right, so I've come to the following value. So this gave me a 5.25, okay, and this is a 1.25, this is negative 0.75, and this is also a negative 0.75, okay. And so now I'm going to put in the graph, okay. I'm going to put all of these plotting points on the graph so that we can see what's going on. Now, my graphing space is going to interfere with some corner of this board right here, so forgive me if that's the case. All right, so now let's look at the graphing space right here. So as we're at negative, okay, now when we're at negative 1.5, this is about right here, negative 1.5, okay, negative 1.5. All right, so it has that point popped out right there, which was that positive 5.25 as seen in that table values earlier. And then now let's move on to and so it seems like this point that we just newly added in was consistent with that that tracing work that we were doing earlier. Okay, you see, so now I was tracing that graph. Think about some electronic pencil that was tracing here. Then that point still on that trace, still on that path right there. Okay, and now let's continue. So here at negative 1.5, we already had an output at, how about negative 0.5 right here? So negative 0.5 right there. And now that what just popped out is that value at being at 1.25, just consistent with what you have seen on the table values earlier. And then we come down to, so how about positive 0.5, okay? So positive 0.5. Okay, and now we have that value being negative 0.75. Agree perfectly, everything agree perfectly with that table values we've had on the table earlier, on the board earlier. And now let's look at positive 1.5, which is, see, right here on my x-axis, positive 1.5. Okay, and now I had another point that popped out being at a negative height right here. Okay, and then for the next one, let's look at how about, I didn't do this earlier, but how about let's put in a 2.5. How's that? Okay, let's put in a 2.5 right here. Okay, so 2.5, it popped out a point right here where the calculator, the software here shows the height being a 1.25 right there. Okay, so on my table values, okay, we can also put in a 2.5. Right, and it gives me a 1.25 again. Okay, and so now back to this graphing space that I just now popped out right here. Now we are ready to put all of these pieces of information back. So now we're clear that we can just start doing that tracing again. So all of those. Now as I'm redoing the tracing, okay, all of those points, even with the new points we put in, they're all perfectly on that shape, okay. And now even without putting in that red trace, like that red tracing work, like that, all of these green points already seem to form perfectly into that nice bent curve, okay. So in case you have heard it or in case you haven't, but yes, that is a quadratic. The graph of a quadratic function. The shape itself is called a parabola. Okay, this shape right here, like a cup right here. Okay, it's called a parabola. All right, but the function itself here is called a quadratic function. You might have seen it. You might have not seen it. The point now is that I just want you to have a general understanding about we shouldn't tie our attention down to, is this going to be a quadratic function or a linear function? That's not the point of this lesson. The point here is just to bring you into the general understanding, that fundamental understanding of what a graph does and what it means by representing a function by a graph. Okay, and then this example illustrates the idea that's why we have those graphs when it comes to a nice smooth curve or a nice line right here, because this kind of function, these kind of function, we have infinitely many values. Those green points on the table of values will never be enough. We can have infinitely many other points. And yes, the whole red curve you are seeing in your in that graphing picture right there, the whole red curve right there is supposedly the place that contains all or the comprehensive trace of all those values. I mean, like I said again, between -2 and -1, I skipped a lot. Maybe I put in -1.5 additionally, but I still skipped infinitely many other values. And so imagine if you put all of those inputs values in there, then you're no longer with a scatter graph anymore, but you're working with a nicer, smoother curve. It could be a curve, it could be a straight line, it could be a straight line rising up and rising down and falling down. But that's the idea, because for a function that has a specific rule given as a formula like this, given as an expression like this, then we can have infinitely many inputs. And so the trace of all of those inputs with outputs together, the trace of all of those plotting points makes up that nice graph right there for yourself. All right. All right, and so that now that you have a clear understanding of what it means by representing a function by its graph, okay? And so you have seen through the two earlier examples that graphing any function, if we're doing that by plotting values like that, constructing a table of values, the process is very solid. However, getting that done takes a lot of time. And for the rest of the time that we're learning pre-calculus here, there will be a lot of functions given at you, and a lot of those we need to see the graphs. A lot of those we have to see the graphs. So there has to be a better way to quickly graph. Okay? And so, yes, this is now a good news. This is now a good news for all the pre-calculus students or all of the college algebra students, because I show you the two earlier examples where we have to build a graph, where we have to construct a graph from scratch so that you can maintain a fundamental understanding of what graphing a function means. But now, at this point, I can tell you the truth that when you arrive at a pre-calculus course, a pre-calculus math course or a college algebra level, then you are allowed to use a graphing calculator, to use a graphing device to assist or to quickly get you a graph for any of your function. Okay, and so allow me to show you a couple graphing devices that I found useful out there. The first one I'm about to show here is the TI calculators that are widely used throughout any classroom, in the nation here, at least in the United States here. Okay, and outside of the TI calculators, allow me to show you another tool that I myself personally used it throughout a lot of my lectures, my video lectures, when it comes to time for graphing. Okay, and so I will show both of those, and then you can also find your own, especially if you are taking classes, math courses as an online math courses. Right there, then you have all of your you have all of your freedom to look for your own favorite graphing calculator device right there. Okay, and so now let me recall the two examples I brought up where we had to sketch the graph by hands. Okay, I mean I was using software in the back, but that was describing the idea of if we were doing it by hand with process. So the first thing is you have the function handed to us, and then we construct a table of values that we have to do manual calculation, and then we put the points on the graph. Okay, x with y value, x with y value, inputs with vertical outputs, inputs with vertical outputs. Okay, that's how we get the graph. But now let's see how fast and how convenient a graphing calculator can do that for you. But see, so you have to keep it in the back of your mind. There's a reason why I always, anytime I teach graphing a function, I always start out teaching the students how how to graph it by hand first, by doing the formal process, as you have seen in the earlier video lectures, because I want you to maintain that fundamental understanding, and then seeing getting an actual graph that's done by a technology is only an optional step to verify your work, and sometime when you're in a need that you have to quickly get the graph, then that can quickly help you get the function. But in the end, I still want you to maintain. Any instructor would like their students, his or her students, to maintain the skill to understand the fundamental of graphing. Rather than just leaving it all for the calculators, leaving it all for the devices, for the technologies. Okay. All right. So now let me first introduce how you can graph those two examples, but using the TI calculator. Okay. And so, all right. So now let me show you how to use the TI calculator to graph that function in example 2 right there. Okay. All right. So here is a TI calculator. I use the simulation of the this. It's a simulation that runs on the computer, but it should work just like your standard TI 84, and the 83 also looks the same. This version I'm using here is a TI 84 plus CE, but all of the key structures look exactly the same, and the functionality will be exactly the same as well. Maybe this version just has a little more memory and a little more power, that's all. But no extra features, okay, as when it comes to graphing. All right, so now when this is your main screen, your main home screen right here. So to graph your function, let's look at that function in example 2 that we did. Okay, so example 2 was f of x equals the x squared minus 2x, the x squared minus 2x. And so this is one fundamental with when you work with any technology to get a graph, you have to find a way to input this function into your technology. Okay, it doesn't matter if you're using your TI calculator or your HP calculator or your Casio calculator, or even any software the programs that you are using over the web right there. There has to be a way to input your function, to provide your function to the software, to the technology that you're using. So for the calculator here's how we're entering the function into the calculator. We're going to hit, you see, for the TI 84 calculator, then we're going to use that y equals key right here. Okay, so quick clarification. The reason it's y equal, because see, at this point in your understanding about a function, we have that notation, see, in equation notation that I have introduced in earlier video lesson. Then y equals x squared minus 2x. So this is how the calculator, your TI 84 calculator, understands the function f of x is x squared minus 2x. Okay, and so now back to your calculator. Okay, your calculator is strong enough to draw 9 different graphs, 9 different functions, 9 graphs of 9 different functions. Okay, and so we only need to draw the one with x squared minus 2x here, so I only go with y1. But see, all of these y1, y2, y3, and this version, maybe the stronger feature of this version, it has the capability to color my different graphs like that. Okay, it provides up to like 5 and actually 9 different colors like that. Okay, so I'm going to choose y1. So y1 here, it's x squared minus 2x. So the x is the variable. Okay, the x is the variable. So we have to select that key right here. Okay, it's the part that's a lot of time being confused and in students like that. Students will a lot of time mistakenly look for the x alphabetic key, but that's not the one. We're looking for this x right here. This is the variable x right there. Okay, it has different functionality. So if we're using a machine, we got to know how to communicate with that, with your machine properly. So now I'm going to go x, okay? So y1 equals x, but now our function is x squared. So the hat key here is to make it a power, okay? And so now x squared, okay? And then now with this advanced software, with this advanced TI calculator, then then we have to hit the right arrow key to exit out of the superscript mode right there. So now x squared, now we're done with x squared. Now I'm going to type in minus, just that minus key, minus, okay, and then 2 times x. This calculator, all of the 84 calculators are smart enough to know to skip the multiplication sign. So just type 2x, it will know that it's 2 times x. In the older one, like an TI-83, you have to type 2 star x. So 2 times, it gives a star, and then x. This is how it looks in an older version of it, like a TI-83 calculator. Okay, but now back to the, all right, so one more time, x, okay, hat for power 2, and then exit out of that, and then minus 2x. Okay, so that's your function. Now simply just hit enter. The function has already been input. Okay, and so now that you have that function input, y equals x squared minus 2x. Okay, and so now back on that calculator again. So now to see the graph. So just now we just, provided the function into the calculator, have it stored into the calculator. We don't have to worry about hitting a save button or anything like that. It's already stored in the internal memory of your calculator. So now I'm going to go, you see, look at the keys above here. I'm going to click on that graph key right there. Okay, and all of the TI-83, 84 calculators will have the exact same key structure right there. So the graph key is that top line right there. Okay, so now I'm going to click on graph. All right, so there we go. That's the graph of your the function x squared minus 2x like that. And it looks just like the graph we have already achieved back in example when I was doing example 2 manually, when we were graphing it, constructing the graph step by step. Okay, and then there will be ways to adjust the zooming and the window feature of this. And I will save all of that detail learning for as we go through in the quarter. But for now, at least, if you want a closer look at the graph, then we can click on the zoom button. Okay, we can click on the zoom button, and then you can zoom in. Okay, you can zoom in, up and down for selecting zoom in, zooming out, or zoom square. Now, let me quickly explain about this zoom square right here. Z square is for zoom square. Okay. Because right now your calculator does not put, you see, look, this is a 1 on the x-axis, on the input axis, and this is a 1 scale on the y-axis, on the output axis. Okay, and you can see that they're not in square, they're not equal scale right here, and that's the idea. So back to that zoom button, you see this feature number 5 right here that says zoom square. We select that option if you want the scaling on the vertical axis and the horizontal axis to be exactly the same scale. So now if I select that, you see now it's all in equal scales right here. So now it's put our graph in the actual scaling. Okay, and then you can zoom it in closer. Okay, option 2, we zoom it in, and when you put it in by default, we zooming in with that center point at the origin. So I'm going to hit enter. It's not going to zoom in. It's zooming in, focusing on that origin. X equals 0, y equals 0. And that's how we're doing it. Okay, but you can also choose to zoom in, taking that point as a center by moving this. Okay. Okay, right at 1. And see, from this machine is not always, it's not exactly, won't do the precise job, but see, we can zoom in again, and that zoom in right there with that part. And now if we want to zoom out, we can just click on zoom, okay, and zoom out. Okay, and then we can go back to the right, and that's how we zoomed out. All right, and so that's how we graph this function using the standard TI calculator. Okay, because a lot of time later on throughout the quarters, throughout the time we're learning pre-calculus together, there will be a lot of times that you have different functions, and a lot of functions come at you. Okay, a lot of functions will be given to you. and then you will need to have a way to quickly get the graphs. Otherwise, it's going to take a lot of time to just construct the graph for one function, like how we did that in example 1 and example 2. So example 1 and example 2 only intended for you to understand the fundamental of the graph, in case we're going to get into some function that forces us to explore things completely from scratch. Otherwise, if you already know these functions, just quickly use your calculator for that. Okay. So the same example 2 right here, the same graph for this function y equals x squared minus 2x. Okay. Remember we built a table of values. Okay, so in case you want to see the table of values with the TI 83 and 84 right here, this is how it looks. Okay, so now you want to see the table of values. You see that there are these there's that table word right here, label right here, right above that graph key. And to access that feature, we're gonna go second graph. So second graph. This is the table of values. So look at all of these right here, and then this is the input and this is the output. And so right now your graph is your TI calculator. Your calculator deliver these inputs in a jump of 1, and it started out with 0 over here. Okay, and these are the corresponding outputs right here. And let's find out how consistent that was with our table of values earlier. You can now double check with that. Okay, and you want to see the negative outputs, negative inputs. They are here. We keep scrolling that up. Okay, all right, and so now notice there's a little instruction right here. Say press the plus key for this funny symbol means delta, or it means a change. It represents the jump, because right now each jump is by default a 1. So from -3 to a -2, it's a jump of 1. From -2 to -1 on the inputs column right here, it's a jump of 1. So this delta right here means that if you want to change the jump value, then we're gonna use you're gonna hit the plus key. So now let's hit the plus key. Okay, so hit the plus key, it gives us this, and this is how we're gonna change. So if we want a better refinement, okay, if you want a better refinement, then we set a smaller jump between the values, and you will understand what I mean when we get it done. So now back to the table, I'm going to change this to a 0.5, 0.5, okay, and hit enter. All right, so now observe how it changed right here. See, the jump between any two consecutive values are going to be just only a jump of 0.5 right here. So from minus 2.5 to 2, minus the 1.5 to 1. See, that's what it means. That's what I meant by it's a jump right there. Okay, so now it's a very comprehensive list. And it's not showing, see, even with the strong calculator like this, it still did not show all values out there. It's still leaving a jump. But at least this jump will already gave us a good amount of points enough. Okay, so it's all about, even for any technology, it's all about the best we can go with. Okay, so this is table of values formally. Okay, so once again, from where we were right there, right, to access table of values, here we click second graph, and that brings up the table of values. And in case you want to change the jump so that you can quickly see the table, the more refinement of your table, then we click on the plus sign right there. Okay. All right. So now, outside of this technology, outside of this TI 83, 84 calculator, outside of this technology, allow me to show you my favorite one, because this calculator, I just simply don't like the resolution of the graph, even though it keeps, the company, the manufacturer who made this calculator keep improving it, but it's just maybe me personally, I like a very fine looking graph right there. Okay, so I use Desmos. So I have been using Desmos throughout all of my video lectures here when it comes to graphing. So you can find, and it's a free resource actually. You don't have to spend money to buy Desmos. Okay, so you can find that as Desmos, www.desmos.com. Okay, and it may or may not ask you to open an account with them. You don't have to. Okay, just use it as an anonymous user, it's going to be just fine. It gives you any graphs you need. But so Desmos.com right here. That's the website that you can pop up that graphing calculator I've been using throughout all the video lectures. So now let's switch over to Desmos right here. So now when you're in Desmos, this is what you will see. Okay, there's a graphing space. Okay, and as a matter of fact, let me roll to the beginning to show you how it really looks from the beginning. Okay, so as we type in Desmos, okay, the main page is going to look like this, and there's that button that says the graphing calculator. We go there, we click on that, and it pops out that graphing space right there. And then it has that button right here where you can adjust some settings. So earlier I was putting this where it's making the lines a little more heavyweight, and I skipped out all of the minor grid lines right here. Desmos has a really nice grid feature and very exact and very good looking. Okay, and we keep the axis number. I uncheck that minor grids. I put the steps here, so on the axis, right? See, and once you are in Desmos, then Desmos is highly recommended to be used when you're on a personal computer or on a Mac, on a PC or on a Mac, when you're on a computer. Because with a mouse, then you can scroll the mouse up and down, or you can click this button up and down right there. Okay, that zoom in and that zoom out. Okay, similar to the zooming feature with the TI-83 and 84. But see, so doesn't matter how you zoom, and the more you zoom, it shows you the refinement of your X and your Y axis. But now, you might want to, a lot of times you might want to click on that graph setting button and change the step here to 1 on the x-axis, so that you can see now it shows all of the refinements of each scale of 1 right here. And by default, the Desmos already left your graph in the scale of 1. So if you click on step 1 like that, okay, then that shows all of that, all of the grids in step 1. Okay, and then if you want to see the arrow, then you go graph setting, click on the arrow, check that arrow button, and select this key right here. Okay, and that so now once again, you see Desmos a lot of time by default. Desmos is assuming the vertical axis is the y, and then the x-axis is the horizontal axis. But then you can also remember I explained earlier that the horizontal axis is mainly meant to be the input axis, and then the vertical axis is mainly meant for the output axis. So you can give it whatever label that depends on how you want to. So if you call it the t-axis, then now that's the t-axis. Okay, and then if you give it a label, S right here, then this is the output axis right here. So it's T and S. But for Desmos itself, internally, it always understands the horizontal axis as the x-axis, and the y-axis here to be the vertical axis. And then normally we don't need that. We can just clear it out. Okay, so that's some basic operation with Desmos. So now how do we input a function into Desmos? So now we can just look over to this space right here. Okay, this space is where you inputting all of the functions and all of the equations so that it can instantly pull out a graph for you. Okay, so now again we're working with this function right here, being y equals x squared minus 2x, x squared minus 2x. So, and now as I'm going along, you will see the reason why I really favor Desmos over many other technologies. Like it's quick and it's portable and it's powerful enough. So, all right, so now with Desmos, to see the graph standard notation, we can go like this, just F with parentheses, and you can just simply use your standard keyboard like that. So F, open parentheses, X, close the parentheses. Don't worry about any of these that pops out yet, because I did not complete my command yet. So right now the function is f of x. Hit equal. It looks just like how we were doing it on papers and pencils. So f of x equals, so now x squared. See, if we stop at x, f of x equals x is already a function. So Desmos already quickly put out the graph of a function for us. But this is not the function we're looking at, so let's not worry about that. I'm going to go back to this, make a click. Now I use the hat key to raise power. Okay, and now I'm going to put in a square. Okay, so f of x equals x squared. This is the instant. Desmos already instantly put up the graph for f of x equals x squared. But wait a minute, this is not the actual graph that we were looking at in example 2. So I'm going to click on that, okay? And by the way, in case that your cursor is right at the superscript mode right here, then you can just simply hit on the right arrow key, and that exits out of superscript mode and brings it to the next term like that. And now I'm going to hit minus, okay? And since now we're back to incomplete of your function, so Desmos hide away that graph. Now it's 2x. All right. So now that's the complete function. So f of x equals x squared minus 2x. That's the graph. Okay. Nice and easy and fast. Nice and easy and fast. And then so outside of that input, you can just simply, you see how my mouse cursor is changed to a little pointing finger, index finger pointing right here. Click outside of that, it pops out another command right here. This is where you can type a different function. Say if you can name g of x, okay, equals x minus 2. See, the graph here is going to be printed in blue. That's the graph for the g of x equals x minus 2. It's another function. And then the one in red right here is f of x equals x squared minus 2x. And if you want to delete out a graph, you can click on that. Okay, but right now I don't want to actually. So if you want to delete out, we can just click on that X button right there. It will delete out. Okay, and then now in case you don't want to show this graph, but you still want to keep the function here for other purpose, okay, then you're gonna just click on that icon right here, and it will hide the graph away. Okay, it will hide the graph away. All right, so that's how you can quickly get the graph. All right, so what about when it comes to the graphing creating a graph when a scatter point graph like what we did in example 1? Sadly, I'm not too comfortable with the TI-83 and 84. I'm sure there's a way to show a scatter point, a function, the graph of a function, but only showing scatter points like what we did in example 1, meaning we only have a table of values and then show the graph. Sadly, I've never spent too much time with that kind of calculator, so allow me to get straight with Desmos right here, and Desmos is powerful enough to show you the table of values for any kind of function, either defined as a table or as a function. Okay, so now with Desmos, okay, and I'm still leaving this here, but I want to show a different graph or a different function. So recall from example 1. So our example 1, if we had a table as following. Our example 1 had this table. This is for example 1. Okay, and we were having x being 1, 3, and 0, and then this column was f of x, and we can call that g of x or whatever. But so now it's 2, 7, 1, and that was the input. These are the outputs, and that was the input right here. So now a table like this surprisingly can be done quite easily with Desmos right here. So now let me bring back Desmos. So now, of course, if you want to still retain this earlier function, x squared minus 2x here, then just create a new command entry line right here. Now I'm going to click on the add item, okay, and then click on table. See, so once again, if you want to still maintain this, then leave that there. Click outside of that space, okay, and now click on add item, okay, table, and now it pops out a table like right here. So now x1, see the whole idea about x1 and y1 here is simply because in case you want to have more than one table, then x1 and y1 means a table for one function, and then x2 and y2 means a table for a different function. So now our input values were 1 for x, 3 for x, and again a 0 for x. Okay. And now I'm going to use my right arrow key to navigate over to the right hand side column. Okay. And now I'm ready to type in the output. So the output here is a 2 when x equals 1. So type in 2. Now that's how I see that point just popped out. And this is that little secret that I was doing when I was working on the graph of example 1 right there. Okay, and now when x equals 3, we have an output being 7. So that's our table of value. So when x equals 3, y equals 7. Okay, and then x equals 0, y equals 1. Now we have that point, and this is that little secret that I used right here when I was creating the graph in example 1 and example 2 right there. Okay, and so that's how we're doing. And again, I just want to re-emphasize the fact that, see, even Desmos is smart enough to know that, you know, the input doesn't always have to be x and the output doesn't always have to be y. So if you don't want to be x, you can call that you can call the input here the t variable. Okay, and then you can call the output here. And by the way, I'm using I can just click on that and highlight. Okay, and so the output you can call it w. Okay, so t is the input, w is the output. But now one thing that Desmos will stay permanent with, the right hand side column is always to list the outputs. Okay, and the left hand side column is always to list the inputs. So left hand side column is the input, and the right hand side column is the outputs. That's one thing you got to keep in mind when you work with Desmos. Okay, but whatever name of the variable you want to call for inputs and outputs, you have your choice on that. Okay, so now that's how we have. Okay, and so that's how I use Desmos to get the table of values for example 1 right there, where the function itself was also simply a table of value to represent the function. But now what if, now Desmos is actually, and that's the reason why I really favor Desmos over many other graphing technologies right there out there. But what if we want to use, what if we want to see the table of values for this function right here, with a function like that? Okay, so now let me show you. Now I don't need this table any longer. I could just clear that out. Okay, and there was a whole reason why I still leave this here for now. So the function that we used in example 2 was f of x equals x squared minus 2x. Okay, I'm going to need, but now we want to see the table. We want to see the table. So this is what I'm doing. I'm going to click outside of that command. I'm going to click plus to add item. I'm going to add a table. Okay, so just by default, it shows you this x1, y1. Now over here, instead of typing y1, you can just type f open parentheses x1. Okay, and now notice the logic of Desmos is that once you have defined the function f elsewhere, then anywhere else later when you use that function f, then it will know to use that function. And that's the whole point of learning about function. Once it's defined and given, then anywhere else machine use it that way, the same way how we're doing it. Anywhere I see f, okay, then that means it takes this formula. Okay, and so now I used we can start out with -2. Okay, and see Desmos quickly calculated, and this is the output for -2, and that gives that point right there. Okay, and then I'm going to hit enter, and I'm going to go -1. Okay, and this is when x equals -1. Desmos quickly calculated the output value and gave us that point right here. Okay, and now here's another thing that in case when we are graphing a function like this, then this is the feature that I really like about Desmos right here. Desmos already recognized the jump between these two values, and so the next time all I have to do is hit enter. Desmos automatically generated that value for me where it made a jump in the inputs for being a jump 1. See, so -1, 0, and I hit enter again. Okay, it gave me another input being automatically at a jump 1. That's why, see, x equals -2, x equals -1, x equals 0, x equals 1, and then x equals 2, and these are all the corresponding outputs that came out. And x equals 3, all I did was simply hitting enter so far, and then these are all the plotting points, and that's how we're doing it. Okay, now so the only one thing that it's not as convenient as the TI calculator when it comes to changing the the jump, then if you want to jump, you have to plan for yourself ahead of time. So right now, when I was, if you're just deleting out all of those, and when you were in the beginning, if you want to decide to go with a jump smaller than 1, then start out with your first input. Now the next one is a negative 1.5, so now Desmos will recognize. So it's just not as quickly to change the jump, but you have to go delete the whole thing and start back from the beginning. Okay, and then now with that jump being recognized as a 0.5, then the next one here, Desmos we know, and then we keep now hitting enter, and then Desmos will give the values that come out accordingly. Okay, and that's how we get Desmos. And now once you want to see the graph to be put together, Desmos can do that. Okay, so now just simply click on that. Click on that. So now the graph is shown together with the plotting points. Okay, and so those are the tools that I introduced, and those are not the only tools where you can do graphing. Now there are no specific requirement about which graphing device you have to use, because we use graphing devices here just to help you get a quick graph sometime when it needs to. But in the end, I still want any of my students to understand the actual fundamental of how you make a graph. Okay, so that you have a nice and clear understanding. But admittedly, later on throughout my later lectures here, there will be a lot of times I will have to bring out instant graphs, and that's where I use Desmos, and with your proper understanding about the fundamental of graphing, then you should be able to use Desmos to verify my own graphing of how I came to those graphs, and that saves me time to reconstructing any of those graphs in my future lectures to be from scratch. Okay. All right, and now that once you have come to be fully aware that any graph, any function can be represented by a graph or can be represented as a graph, then let me now introduce you to another example right there where it demonstrates the idea that we can read a graph given or read a function that's represented as a graph given to you, and we're going to read that graph of a function and then be able to evaluate a value. Okay, so let's get started with the wording of the problem right there. So now here we are at example 3. All right, so the instruction of this problem is saying as following. The wording description of the problem is saying as following. The graph of f of x, so some function. Here it's not given as an f of x equals x squared, it's not given as f of x equals 2x minus 1, there's no specific formula. And let's finish with this wording instruction right here. So the graph of f of x is given. Okay, and so now in this way right here, now admittedly, I'm not skilled enough to draw that hand sketch of my tentative graph here, so allow me to use a computer software and show the graph right in front of everyone. Okay, so in an up-close shot right here, this is what the graph looks like. All right, so this is the graph of some function. So this is the graph for f of x. Okay, and I can move it a little bit, move it around a little bit. So this is the graph that represents, to be precise, precisely speaking, this is the graph that represents the function f of x. So we don't know the actual function. So back to what I was saying earlier, we don't know whether it's an f of x equals x squared, is it an f of x equals 2x minus 1. That's not the big matter of this problem right there. The main idea now is that the function was already given and now represented as a graph that you have seen previously. And so now let me put that graph in a corner of our screen right here. So the graph given here represents this function. Okay. And so now here it comes the first question regarding this graph. So now once you have that graph given, let's see what we can do with that graph. So this is the function notation. The inputs is the x variable, and then the output is the f of x. And so again, as a reminder about the meaning of when you're looking at the graph, then when you're looking at the graph, the input values are being placed on the horizontal axis here. And so since the function here is naming the input variable as the x variable, so now what? It's this axis here, this horizontal axis here should be labeled as the x-axis in case any one of you is taking notes and trying to duplicate this graph on your own notes paper over here. And then the vertical height, the vertical axis here is a place to represent all of the outputs, okay, or all of the output values of, corresponding to each x. Okay, so in that way, now we want to evaluate. So from the graph here given, from the graph that represents the function f of x and the graph given, we want to evaluate. All right, we want to evaluate. So how about f of 4? Okay, f of 4. F of 4. So now in function, so before we dive into that graph right there, this notation from what we've learned previously prior to getting to this point of studying about the graph and reading the graph, reading a value from the graph, then this, at least from what you all have already understood, then this notation tells us that this function right now, we want to look for the value of f when the input value equals 4. So what's the function value? What's the output value of your function when x equals 4? Okay, but now we cannot build a table of values because we don't know we don't see the actual rule of this function, and the only way we see is the graphical representation that you're seeing here. Okay, so now in this way right here, in this situation, then this is how we can handle it. Okay, so with now the graph given, so again, as I said earlier, the input values are being placed on the horizontal axis. And so now specifically the function, the problem is asking for evaluate the function value when x equals 4. So now first thing in line, we're looking right on this x-axis, right on this horizontal axis. Try to locate x equals 4. So x equals 4 is right about there. Now be careful with the way I'm saying. All I can say is right about there because that's what I can see. That's where I can see where 4 is. Okay? And so now when x equals 4, so right about there, now the output, again, the output is represented as the height. It's just like an international convention at this point that the vertical height, okay, the vertical value, the vertical coordinates represents the height, represents the output value of your function at that particular x input. Okay, so now in that way, at x equals particularly 4, our output here, our height at that point, is 1, 2, and 3. So right now on my eyes, according to my eyes, from what I can see right in the graph, then it's about the height there, that output there is estimated, is about 3. Okay? So 1, 2, and 3, and we can see the Desmos that I'm using here has a very nice grid right here so that we can follow with the grids to make as precise as possible about how far these output values are. Okay, so this is about 3, right there, 3 grids up. Okay, and so let me put it in a closer zoom so that anyone would have a more convincing view right here. But when x equals 3, the output of the function f of x, so now when x equals 4, I mean then the f of 4 equals 3. All right, so now we are ready to give an answer, and that's all there is. So it took me some time to explain, but that's all we're trying to get. So now I'm saying my conclusion, and that's about the best we can go. That's about the best we can go. So f of 4, now I can say it's about 3. It equals 3. Okay, and so now I start using that term a little loosely now, and it's about, I keep saying about or estimated. That's another truth about these kind of problems, that we're trying to evaluate a problem, but we're trying to evaluate a function output value, but entirely based on a given graph. Now, the problem itself very commonly is worded as evaluate the function value, but the other truth of that, another truth of that, the best truth of that is that for this kind of problem, all it was behind the scene was to estimate. So watch out that sometimes some textbooks, some problem also word the exact same problem as estimates, f of 4. Okay, that means we're simply looking at the graphs and see everybody's eyes are seeing things differently. So I see that outputs, that vertical height being a 3, somebody else might see that as a 3.5, somebody else might see that as a 3.01, somebody else might see that as a 2.99. Okay, it all depends on how people are seeing it. Okay, so another way of saying that, and more precisely, when it comes to evaluating a function output value, right, from a given graph, it's more like we are estimating the value from the graph. So when x equals 4, when x to be about 4, then the function, the height of that, okay, is about 3. All right, and then now I also need to mention another property that, so see, when x equals 4, okay, and together with the outputs, that's why we have a point, and that point is being right on C, and even I'm trying to use the tracing feature, it's not getting me the exact point as well. But see, therefore, with the height, when x equals 4 on the x-axis and when y equals 3 on the y-axis, we have a point, and that point stays right on the graph. And again, that's the whole idea about using a graph to represent a function, okay, to represent the x and y, the input and the output values of a function. Okay, and so now let's look at part B of the example. So now pretty much very similar work. Now let's look at how about let's evaluate, and now I call that part B. Okay, let's evaluate. So how about f of -2. All right, -2. Okay, so again, now once you've had some good experience and once I've spent some good amount of time explaining what's going on, let's pick up the pace here. So now on our graph, which is still being displayed here in the corner of our screen, and I can put it in a zoom, a closer zoom right here. Then when x equals 2 on the x-axis, when x equals -2 on the input axis, when the input is -2. Let's see, and this is what I emphasized, what I really tried to emphasize here. It's starting to become a little unclear to know exactly where the height is. Now, thankfully, the program I'm using here has a very nice zoom feature. So the closer we zoom in, the more convincing it is that the output is +2. But see, in a further view, where it's a little bit harder and more challenging to see, then all I can say is that when x equals -2, when the input is -2, we have the output being about +2. Okay, all right, so that means now I can make that conclusion from reading the graph. Okay, f of -2 is equal to +2. But see, even though we write equal to, make it seems like it's an exact value, but it was all about we were estimating the best the best that to our best capability. Okay. All right, and so now let's look at part C of the example, and pretty much I'm repeating the same kind, or maybe with this problem, let's leave that for viewers, okay, to still have a look at the graph right here and be able to tell. Okay, so how about for the viewers, for the students who are learning with me to get some experience, how about I would call this problem an FYT right here, which is for your trying. Okay, so let's try independently on your own, and the graph is still here. F at how about 0? Okay, f at 0. All right, so I'm gonna wait for a little bit, and I will only tell the final answer, and then I'll leave that for you to verify, because this is an FYT right here. All right, and so the answer now should be, and in my estimates, -2. Okay, and so this is the answer. Okay, and I hope your estimate agrees with mine. But in the end, it's all about we're looking at the graph, right? And we're looking at the graph and be able to read from the graph and tell us about the function output values right there. All right, and so now let's look at another type of problem. So still we're in example 3. But let's look at, so we have the graph given, but we want to find, let's say this is part C of the example. Okay. Find x find x satisfying. Okay, find x satisfying. And x here in this function, in our function, in the role of our function, x is playing in the role of the input. So find the input value that's satisfying f of x, okay, equals 4. All right. I want to find the value for x. Okay. Satisfying f of x equals 4. Okay. So basically, so this is what the function is. This is what we're doing with this given graph right here. Now let me put the graph in a closer zoom right here. So we want to find where is it. We want to find out where is it on the x-axis, on the input axis here. That we want to find the x values that's satisfying the output. See, because now again at this point, anyone learning in this video lesson should be fully aware that this value means the vertical height, okay, because it's equals to the output. So we want to find where on the x-axis gives this height being 4. Okay, where on the x-axis that the function output equals 4, and the function output is again the vertical, the value of the function, the vertical coordinates. All right, so now in that way, let's search for it. And again, anytime we're reading things from a graph, then the best we can go is just simply to estimate. Okay, and so now, so mainly as what we desire, then we want the function output to be 4. So 4 is about here. Okay, 4 is about here. And so now I'm gonna put in this line right here. So think about this grid right here. This is 4. Okay, so when at that height being 4, well, let's draw a horizontal line. So let me quickly put in a line right here. All right, see that line in green that just now popped out, or maybe I can change the color to black right here. But this line in black, or maybe I can also make it dotted line because it's not really the part of the graph. It's just now we use that as a guideline. So now this horizontal line represents the height being 4. Okay, the height being 4, because anywhere here we have a height reaching from the axis, the input axis up to that height of where the dotted line is. That's the height's 4. Okay, so now we want the output to be 4. So now where on this graph, or at which x-axis will this line cross with the graph? So this line, in dotted line right here, cross with the graph at about x equals 6. That's one of it, at about x equals 6. And then here, see, another, the one here to be estimated. See, right here, okay, it seems about what it seems about, and the best we can go, okay, using a tracing feature right there, about a negative 2.449 or something like that. Okay, and that gives a height 4, so about negative 2.449. And this is thankfully that we have a powerful software, but see, about negative, about somewhere past, somewhere further out than negative 2, that's fair enough. Okay, so in that way, now I can say for this problem, okay, reading from the graph, right? And so it leads to, this is why I'm using arrow over here. On one value we found the satisfying x value here is 6, and the other one is about negative 2.449, and that's about the best we can go over there for that. Okay, all right, so that is another kind of problem that can be introduced here, that showing what we can do. And throughout the rest of our time learning together in pre-calculus here, there will be many other instances where we use the graph of a function, okay, to evaluate and to estimate values. Okay. All right, and so at this point it is clear that any function can be eventually represented as a graph. But the problem now is that there are so many graphs out there. There will be so many graphs out there, and the graph of any function, as you have seen, so in some of the earlier function that we have already learned to graph and learn looking at the graph, then this is the graph that represents one of our function in the earlier example in this video. But what I was in the middle of saying earlier is that, as a matter of fact, a graph on its own, it's just simply a curve. Okay, so yes, our function that we have seen in an earlier example has a shape like the one you are seeing right now. But will any curve out there be the graph that represents a function? For example, now there will be time that we will be looking at a curve that loops around like this, that looks like this. Okay, it's a graph. It's just a drawing. It's just a sketch. It has a trace. It has a path. It has a physical representation. But will this representation be the representation of a function? That's the challenge that we are facing right here. And at this point, the reason we're learning this lesson is that because we have seen through the earlier part of the lesson here is that there will be times where a function is simply given already represented as a graph. So we need to learn that skill to look at the graph and be able to identify whether our graph presented here is presenting the graph of an actual function, or not. If not, it's just some any graph out there. Okay, and so in order to answer that question, then we need to look back at the definition of the generality of a function again, or the requirements for being a function again, before we can decide. Okay, and so now let me briefly recall that for any function, and I've in the earlier video lesson I already mentioned that any function has the following common properties right here, common the understanding. So the function itself is a rule. Any function, any function, what we have learned through the definition is the number one thing, it's a rule. And because having a rule, input and outputs, the rule that connects, that relates the inputs and the outputs, okay, it's a rule. But then each input determines exactly one output, okay, and exactly one and only one output. All right. And so just simply looking at a rule that's relating inputs and outputs, and we have learned through earlier part of this video lesson that we are putting the inputs on the horizontal axis and we're putting all the output values on the vertical axis, and that's consequently how we end up with having a graph. Okay, so but then, for example, now let me bring up the graph as following. But then with a graph like this, see, for every input we can set the x values here being the inputs. The x value can be the inputs, and then we are coming out with two outputs. We're coming out with two values. For example, now let me put a vertical line right here to make the grid clear. But when the x equals 2, for example, this x value comes out with two different y value. Okay, so we have two outputs. Okay, whereas in some other graph, for example, with this one right here, okay, then at a particular input, x equals 2, for example, there's only one output. So now, once again, back to the question, which one among these graph choices is that either this curve or is that either this curve that represent the graph of a function? And so in order to make clear and be able to distinguish for ourselves, we have to rely on the definition of it being a function. And so just simply now back to what I was more than halfway of saying, then yes, a function on its truest nature, it's a rule, it's relating between input and output. But furthermore, as another quite important restriction, as another quite important requirement, each input determines exactly one and only one output. And this is the key that now helps us to determine among the different graphs which one can be the graph that represents a function and which one is just simply any other graph out there. So in that way, now let me bring back this graph, and the answer will become a little more clear now. So with this graph right here, let's say when we're at inputs arbitrary x equals -2. And that is why now I'm going to use a vertical line as the most effective tool right now to detect. So the vertical line is placed right at x equals -2 arbitrarily. And then this, as a requirement, is stating, let me quickly put away this screen that's interfering with the definition, but we need each input. So the vertical line I put on the screen was placed right at the inputs -2 arbitrarily. And then at that input, it came out to exactly one and only one output, because we saw on the graph at this input, x equals -2, there's only one output, which is one y value only. Okay, and then, but then not only at that input, what about other inputs? At some other input, somewhere between -2 and -1, for example. Okay, then are we achieving the same goal? One input goes to one output. Now, what if we add a different input right here, x equals 1? At x equals 1, once again, it looks like this vertical line comes out crossing through giving only one y value. Okay, so the vertical line is being placed at, I use that vertical line, I put it in dotted place. Okay, but the vertical line is to make the input value to be clearly recognized. But then all of a sudden later on, when we get further into that, we will realize that it's an effective tool to detect whether a function can be, a graph can be a function or not. Okay, so far, no matter where I put this vertical line right here, because the vertical line again represents an input value, and anywhere we're looking at any input, at an input here, for example, where I'm not even sure what exactly the value is, somewhere between 2 and 3. We're still ending up with one output, one y value. Okay, that's one case. So now this meets the requirements for being a function. So each input determines exactly one and only one output. Okay, so now what about the other graph? All right, so now let me bring up that graph, that other graph. It's a graph. It's a graph. And now let's pick an input arbitrarily. Let's pick an input arbitrarily. So to pick an input, let's say, see, among the graph here, I'm going to pick x equals 1. That's why I put this vertical line right here at x equals 1. Okay, but when x equals 1, and maybe it's even better that I put it in closer zoom. So in full screen mode right here, when x equals 1, anyone viewing this video is seeing that this vertical line right at x equals 1 for the input crosses the graph at 2 y values. Okay, and that's not the only place where that thing happens. And that thing, I mean one input, but ending up with 2 outputs. Okay, other places like x equals 2, that similar situation happens. One input for one x value, we're ending up with 2 y values, 2 outputs. And again, because now in our understanding, we are agreeing internationally that inputs is being placed on the the horizontal axis, and outputs are being placed on the vertical axis, or we call it, traditionally the y values, and then the inputs traditionally the x values. Okay, and then having the graph as a nice smooth curve as described here is not the only case. Okay, so what about let's check it out. Let's check it out when it's a scatter plot, when it's a plot that's being scattered. Okay, so now what about we can have a function that gives a scatter graph like this, a graph with scatter points. Okay, so right now, simply looking at this graph, it's just a set of scatter points. How do we know if this graph here represents a a function, okay? Because outside of this scatter plot, outside of this plot, this graph that contains all the scatter points that's scattering around all over the plane right there, then some other time we have other set of scatter points, okay? So this is one set of scatter points. Now I'm going to put that away. There's another set of scatter points right here. Which one among these two? Which one among these two graphs, okay, represents represents a function? Okay, so now once again we must look back at our requirements. A function is a rule, and because being a rule, that's why we can put x values, input value on the x-axis, on the horizontal axis, and then we can put the output value on the vertical axis, and together we have a point. Okay, so simply having a rule, we can, with that relating inputs and outputs, we can have a point. That's why we have, consequently, we ended up with this. Okay, but then, is it this graph right here or this graph here? So anyone watching along the video, feel free to pause the video to duplicate the graph here on your own notes if you would like to have. Because I'm not fast enough of generating these graphs as a hand sketch, and it's taking your time with seeing me doing that on the board here. So I'm just popping out quickly, popping out with those graphs here. So there has been two scatter graphs already. Okay, but so is this one the graph that represents a function, or is this one the graph that represents a function? Okay, and so in that way, again, now we read further into our definition, then we hit into that requirements again. Each input, so now each x value, each horizontal value determines exactly one and only one output, vertical value. So for each horizontal value, there's only one and exactly one vertical value correspondingly. All right, so in that way, now back to the graph. Okay, something like this. Now I'm going to again use a vertical line. So we only have a few points. So that first point is at x equals 1 and y equals 4. Okay, so x equals 1 and y equals 4. That means the input is x equals 1, and that's the reason why I'm putting my line right at this value. Okay, and then now I'm going to move that, and so there's only one output, which is why we're having that only one point. And then I'm going to move my line to the next value right here, where x equals 2 for the input. And then this here on this line, I see only one y value corresponding to this input. And then I'm changing again to the next input. Okay, I'm only seeing one y value, and then so on and so on. So now for the rest, anyone following along with this lesson should be able to see that for the rest of all of these points, one input comes out with only one output, which is the vertical y value. Okay, now whereas in this version, okay, so now in a different graph that's containing scatter points. Okay, now I'm putting in that vertical line again. Okay, so at the first point, yes, one input gives one output, but let's make sure all of them is the same. I mean, all of them follows the same requirements. So one input comes out with one output. Okay, and then the next one output, x equals 3 comes out with one input, x equals 3 comes out with one output. But now for the next one, at least what my eyes are telling me right now on this computer screen, one input, x equals 4, gives me two outputs. And this is one violation today to the rule of being a function already. We strictly require that each input determines exactly one and only one output. Okay, and so now tell you what, this graph right here fails to be the graph of a function, to be the graph that represents a function. It's a graph. I'm not saying it's not a graph, but it's still a graph. It's just simply not the graph. It's just not the graph that represents a function. Okay, and so just like that, earlier I was showing this nice loop around curve right here. So it's still a graph. It's still a graph. I'm just saying that it fails to be the graph that represents a function. Okay, and so now in that way, throughout all of my demonstration, I've been using that effective tool that's now widely introduced throughout all the professors, including me. We refer to this as the vertical line methods. Now this vertical line method aims at that purpose, to detect which graph represents a function or which graph fails to represent a function. Okay, and so what the main idea now is that we use a vertical line, okay, and then bring it back and forth on the side. Bring it back and forth, left to right, and right to left. Okay, and so we bring it back and forth to detect anywhere that we can violate one input but coming out with two outputs, and that's where the graph fails to be the graph that represents a function. And so in that way, now let me temporarily hide the graphing space away, and so let me now introduce that the general idea with the general philosophy, the general fundamental of that vertical line test to detect which graph represents a function. So this is, and allow me to word it in my own wording right here. So this is called the vertical line test. Okay, vertical line test. So we use this to test whether a given curve, a given graph is representing a function. So here's the idea. The wording says, in my wording it says, I can say that if a graph, okay, if a graph represents a function, if that's so, then here's the important statement: no vertical line, okay, no vertical line crosses the graph. Okay, no vertical line crosses the graph at more than 1. Okay, no vertical line crosses the graph at more than 1 points. All right, so no vertical line crosses the graph at more than 1 point. So that means think the other way around. If we spot a vertical line that crosses the graph at more than 1 point, then the graph cannot be the graph of a function. Okay, so this is a statement that if a graph represents a function, then no vertical line crosses the graph at more than 1 point. But then that means when we are directly using it, we think of that the other way around. If we use a vertical line and the vertical line on the opposite way crosses at more than 1 point, then it's going to fail to be the graph that represents a function. Okay, and so that's why in that way, back in this problem that I did earlier, back in this little graph I did earlier, I placed a vertical line right here, and this vertical line already crossed through the graph at more than 1 point. Okay, see, it crosses through at more than 1 point, and this is why this graph here fails to represent the graph of a function. Okay, to represent a function. Now, whereas, okay, let me put on a different curve. See, this curve right here, in the way how it is, no matter where you put that vertical line, the vertical line you cannot find. See, you won't find one vertical line, you won't find any vertical lines that crosses the graph at more than 1 point. See, anywhere you put that vertical line, it only crosses the graph at just 1 point. Now the grids in this graphing software may be interfering. Let me turn that off. Okay, I'm going to hide the axis number. I'm also going to hide the grids. Okay, so now let's see things in real action, and maybe even for better purpose, I'm going to completely hide the axes right here. Okay, just look at the graph itself right here. Okay, now vertical line and the graph itself. Now anywhere I place that vertical line, okay, there's only one crossing point. I zoom it out, okay, and I keep tracing it back and forth like that, okay, and now anyone is pretty convinced. And now in these days, with the assistance of technology, with the help, with the aid of technology, things become a lot more clear. So this graph here, once it's given, it surely represents the graph of a function. And so now I can put the grids back. All right, and the axes. All right, and so now in that way, let's now head into an example, a formal example where you can have a hands-on experience to quickly determine and detect which graph given is the graph of a function, is the graph that represents a function, or which graph given will fail representing the graph of a function. Okay. All right, so now for our example 4 here, okay, simply the wording instruction says determine if the given graph represents a function. Okay, and so here's the plan for this entire example over here. Every problem we will have part A, part B, part C. Each part of those problems, each part is a problem, that each part is a graph on its own, and we're gonna decide. We're gonna use a vertical line test and decide whether it's a yes or no. And so allow me not to show the graph on this board right here, because I don't want to waste your time seeing my hand sketch right there. So I'm gonna, for each graph, part A, part B, part C, I'm gonna blend the graph on the computer screens right on our screens right here. Okay, and so if you have to, go ahead and feel free to pause the video to copy down the notes, so to copy down the graph, or to take a photo shot right from screen right there, so that you can have a picture. Okay, so now part A, here's the graph. All right, so now we're gonna have a given graph. All right, so on part A right here, the graph is as following. So that's the graph right there. Okay, so feel free to take a photo shot of this graph, or take a screenshot of this graph right here. All right, and now I'm going to put that in small view. Okay, but now the whole idea now is, in order to determine if this graph represents a function, then all we have to do is throw in that vertical line test right there. Okay, and then I can also now once you have this graph, duplicate it on your paper, and once you have this graph, copy on your paper. You don't have to worry about zooming it in or not. The idea is illustrative enough, okay? Because what I'm about to zoom it in, and you don't have to worry about recreating that version where it's zoomed in, okay? But now with this, I'm gonna throw in my vertical line, okay? So here's where I'm putting in my vertical line right here. Now anyone viewing the video lesson is gonna see how my vertical line is moving in to start detecting the crossing. So now right here, didn't cross yet, but now right into that first place where it start interfering in, it's already crossing. So we already found one vertical line that crosses the graph at 2 points. Okay, and so this is where I'm saying this graph fails the vertical line test. Okay, because using the vertical line test in this case. So now back to the problem itself here, I have to note, right? So as a hint here, this is, I'll put a comma here as an extra note. This is using the vertical line test, okay? Vertical line test, and that's the whole scheme of this problem right there, of this entire example right here, where each part A, B, and C, and D is one independent problem on its own. So right now with part A, the graph is given, right? And so now I can say, okay, the graph, all right, the graph fails, okay, fails the test, fails the vertical, all right. The graph failed the vertical. line test. That's it. And so in that way, consequently, it leads to, okay, the graph does not, okay, represent a function. Okay, it's just some graph out there. It's just some graph out there. In other video lecture, I will explain what exactly those graphs will be when they fail to represent a function. But now all we pay attention to is whether this graph represents the graph of a function, and it doesn't. Okay, it doesn't represent a function. So that's part A right there. Okay. And now we're gonna switch to part B. All right, so now for part B, let's look at a different graph. And so now I'm gonna prepare the screen again, and I'm gonna pop it out right on the computer screen right here in front of you instead of drawing that on the board space here that I have. All right, so now in my empty graphing space right here, let's look at this graph. Okay, so what about this graph in part B right here? All right, and now so you can feel free to pause the video lecture, take a Photoshop of that. Okay, and then maybe if you're taking note, copy and paste that Photoshop there somewhere on your notes like that. And now in a smaller view right here, that's the graph. So this part B has that graph. It's a curve, it's a line, it's a drawing, it's a graph. Okay, and now we want to know whether this graph here you're seeing represents a function. Okay, so the only way of doing that, we're gonna use the vertical line test right there. So now I'm gonna put in the vertical line. All right, so in close-up view right here, here's our vertical line. Okay, and I'm gonna be moving the vertical line in. And right now it seems like from where I initially placed my line, it seems like the line here is not even crossing. Now don't worry, it's just because the zooming here is too close. But if we zoom it far out enough, it crosses here. Okay, and now I'm gonna start moving in. I'm gonna start moving my vertical line in. There you go. And now you can see that anywhere I'm moving, at anywhere I place my vertical line right now, or currently at any place, the vertical line only crosses the graph in red here at only one point. Okay, and then the challenge now is that if anywhere we place a line, it only crosses the graph at one point, then we have to trace that. We have to move that vertical line to a different spot. Okay, and so thankfully in these days, since any computer software is powerful enough that we can quickly use a mouse button and quickly move the vertical line back and forth. Now, back in my time when Desmos wasn't around and when TI calculator was not so common back then I have to hand sketch all of the vertical line all throughout the graph, and to make sure that I have seen as many vertical lines as possible, and to ensure that all of those vertical lines I put through this graph here are none of them crosses at multiple points. And so, but here thanks to technology in these days, we can quickly move that back and forth. Okay, and none of the place that we put our vertical line, we spotted a double crossing. Okay, and allow me to use that short term right there. A double crossing means one vertical line but crosses the graph at two or multiple places. So in this way, now our conclusion says, according to our conclusion, I'm saying that for part B, this graph here, okay, this graph passes, because what we just did is we used the vertical line test. So the graph passes the vertical line test. All right, and so consequently it means this graph, okay, this graph, or the graph in this problem represents or does represent a function. All right, so that's how we are using the vertical line test, a pretty effective tool. Okay, and so now after part A and part B, where I really try to explain in detail, now part C, D, and you know, and so on. Okay, I'm gonna pick up pace right here. All right, and so now I'm gonna erase the board here, and let's put in part C. All right, so the graph for part C is as following. All right, nobody is required to know what function this is yet, or what equation this is yet. Nobody is required to know that yet. But what you have here, simply all I'm asking is what you see here is the graph. Okay, and so now we want to determine whether or not this graph represents a function. So now I'm going to put in, okay, a vertical line. Okay, and right there at the initial place where I put in the vertical line, it only crosses at one point. But now let's keep moving it back and forth. I'm going to move it to the left, and anywhere my vertical line goes, it only passes the line at only one point. I mean the graph at only one point. Okay, and then now moving it back to the right hand side, anywhere my vertical line goes. And you can see that all these vertical grids right here is also telling, one of these vertical grids is also telling the story. Each grid right here, each vertical grid is only crossing at one y value. Okay, so if now once we build a little more experience, see we can just place our vertical line somewhere between the grids, and it's still crossing only one point. And so now what does, obviously now we can make that conclusion. Okay, so I'm not going to write down as much reasoning. So it passes. Okay, this graph passes vertical line test. All right, so that's what we recognized. We trace it back and forth enough, and then it leads to, so that means this graph represents a function. All right, so that's part C. Okay, so now let's look at part part D right here, and let's quickly expose ourselves to another graph. Okay, so part D, and here's the graph. All right, so the graph for our part D is here, and once again feel free to pause the video and take a Photoshop of your current graph right here, and copy and paste that somewhere on your notes that you're taking. Okay, and then here's a smaller version right here so that I can also show myself. Okay, so with this graph, once again, it's just a drawing, it's just a curve. Okay, some kind of path that you're seeing. Okay, is this path, is this graph representing a function? The vertical line is telling the story. Okay, so now I'm going to put a vertical line in, and now the story is clear. Okay, the ending is here. I don't even need to move this vertical line anywhere because we have already found it. We have already spotted that at one spot here, at one input here, see, at 4.5, right? The vertical line here crosses or passes the graph at 2 points or more than 1 point. The vertical line crosses the graph at more than 1 point. Okay, so now I'm saying, in my saying right here, I'm saying that this graph fails, right? D is, in D here we got a graph, and the graph fails the vertical line test. And I apologize for keep getting shorter and shorter term right here, vertical line test. Okay, so in that way it means that the graph okay, does not represent okay, a function. That's what it is. Okay, and then once again, let's clear out the board, put the picture away, and have a different problem to look at. Let's have a different graph to look at. All right, so now this time our graph is a graph that contains scatter points right there. Okay, so we have a scatter plot or a scatter points plot. Okay, and once again, feel free to, and the grids are extremely useful here in this case right here, and feel free to pause the video and take a photo shot of the screen right here, or take a screenshot right here and copy and paste that on your notes somewhere in case you are taking notes along with the lesson. All right, but now in smaller view now. Okay, so in part E, this is part E of the example. That's the graph right there. So we want to know if this graph represents a function. Okay, so once again, the only way of doing that, the only way of detecting that and to come out with a clear answer, let's use the vertical line test right there. Okay, so now I'm going to place it in that vertical line test. Right now, it's not even hitting with any points, so that didn't tell the story yet. Okay, that's inconclusive there, but right now, well, that's 1 point it passes, okay, but that's not enough, okay, because it passed at 1 point, I mean, it passes at a place doesn't mean you're going to stop. You're going to have to continue the test, and as long as once you've reached all testing points passes, that's where it works. So let's place our vertical line at another spot right there. Does it pass? Yes, it passed. Okay, what about here? It still passes, right? But what about here? Oops. All right, one input, one x value comes out with 2 y value. Y equals 1, y equals 1, y equals 2. They're both x equals 1. One input coming out with 2 output values. So this is where, again, now I'm saying that the graph here fails the vertical line test. All right, so now in this case, obviously it's implying that the graph does not represent a function. All right, and that's all for this example, and that's how we can detect whether or not a given curve can represent a function or not. All right.